Hi folks, and welcome back to another lesson in BCIT, Technology Teacher Education, TTED 4010, where we're taking a look at doing strange things with Arduinos over the course of this semester. And in a normal non-COVID year, this is my favorite day of the class, because today I usually have students come in and they come into the class and I give each of them a speaker and we solder some wires onto the speaker and we go back into the computer lab after getting things hooked up in the electronics shop and I show you how to plug it in and make a sound, and then I go for coffee. And everybody's like, what kind of lousy instruction is this? And by the time I come back, somebody's figured out how to make their speaker go beep, and then somebody figured out beep boop, and then somebody's got it playing the theme from Star Wars, and then Empire Strikes Back, and then Super Mario shows up, and basically I come back to the cacophony of the Arduino Symphony Orchestra. And it's just beautiful because you're getting to the point now where you don't necessarily need me to tell you every step of the way, but you just need somebody to say, oh, well, here's a couple things to get you started and go explore it on your own. And hopefully you're starting to build up that little bit of confidence with the Arduino. So to get you started, you've got a big bad breadboard board if you're in my class, but if you're not and you just happen to be watching this, you just need a speaker. And I'm going to talk a little bit about speakers and what they are and how they work with your Arduino and why everything kind of sounds like a 1980s arcade. Not that many of you were hanging out in arcades in the 1980s, but for those of us who were, we'll remember the sounds. And anyways, let's get going and let's see if we can get a virtual Arduino Symphony Orchestra up and running. So before we begin, it helps to understand a little bit about sound. Okay, and we know that sound is transmitted through the air, which is why in space nobody can hear you scream. Forget which movie had that as its tagline, but Alien? Yeah, anyway. So when I'm making sound right here, my voice box is vibrating, okay? And so there's little flaps and flanges in there, and depending on how we alter our muscles, we can make our voice box vibrate at different rates. And as we move our lips around, we can control and shape, modulate those sounds that come out of there. And we're creating a wave of vibrations in the air, and that wave of vibrations in the air is coming right here. And in my case, it's hitting the microphone, and it's making that microphone vibrate in a certain pattern. It's moving in and out as those tiny little shock waves of air hit it, and the computer is recording that electronically and transmitting it to you. And somewhere in your computer system, either in your headphones or in speakers on your desk right now, you've got speakers that are vibrating and creating vibrations of the air coming to your ears. So let's take a look at how the speakers actually do it. Now, there's a couple different types of speaker, but our most common style of speaker is, you call it an electromechanical speaker. And we've got a diaphragm right here. And you've probably seen some things where you can take the diaphragm and you can put some dust on it, or cornstarch and water is a neat mixture. Put some saran wrap over top of your speaker before you do that. Mix up some cornstarch and water, put it on the speaker, and just crank the bass, and you get some really neat effects out there. Because what happens to create the sound is that diaphragm moves in and out. You can see when I push on it right there, it's moving in. I don't have a way to pull it out right now. And what makes that happen is at the back of the speaker, we've got a permanent magnet right on here. So this is a magnet. It's always charged, and they're always magnetic. And then sitting inside of that, and I'm sorry, speaker, but in the name of science, we have to take a look inside you a little bit. Let's just go inside this speaker, and I'll save you from having to do this to your speaker. Let's pop this open. And there you can see the wires that come in the back. So the wire comes in here, and it comes down right into the middle of this magnet. You can see where the diaphragm's attached in there. And where that diaphragm's attached, we've got this little piece that is going to move in and out right here. That's what's rocking the diaphragm forwards and backwards to create the sound, is when that moves in and out. That's creating the sound. And the reason it's moving in and out is because in there is an electric coil. And let me just pull this open here. We've got some lovely fabric holding that all together. This one's being a little more recalcitrant than some of them are. There we go. Right down on this side in here, we're getting in there. And you can start to see a little copper coil starting to form. Now, we've probably in elementary school, you can see the magnet's doing its thing. Definitely a magnet. It's sticking to my pliers here. Let's see if there we go. I've got that coil coming out right now. And you can see they've built it very light so that it can respond very quickly. Now, this coil of wire that I've got in my hands right here was previously embedded right in this little ring right here where it's in a field of high magnetic strength. Now, on this coil right here, and this is actually a whole bunch of very fine wire wrapped around here. See if I can get just one little bit of that wire to come off. Break this up. There we go. You can see this is a little bit of wire right in here. And it is some super duper fine wire. In fact, I've got 3 wires right there. That's, see if I can hold that down at maybe if I turn the light and adjust that. Yeah, I don't think I'm going to be able to zoom in well enough for you to get a really good view of one wire. It's too small to display on here, but if I keep pulling it apart, I can get down to one wire and I can put my calipers on there. And I can tell you that wire is almost too small for the calipers to measure. Looks like it's coming in somewhere around about 8 thousandths of an inch, or what have I got on there, 0.1 millimeters. Yeah, it's tiny. So really fine diameter wire. Now the reason we want a fine diameter wire is so that you can get many, many turns of that wire wrapped around that coil. I'm so weak I snapped it off right there. And the reason we want lots of turns around there is because you know this from doing that experiment when you're in elementary school where you take a nail and you wrap a piece of wire around it and then you hook it up to a battery and it becomes a magnet. Well, this coil turns into a magnet when we run electricity through it. And when that coil becomes a magnet and it interacts with the permanent magnet right here, that causes the 2 magnetic fields to interact with each other. And depending on the direction of flow of the current through that coil, it will either move outwards in the magnetic field or pull deeper inwards to the magnetic field. So this little magnet right in here is going to be popping forwards and backwards right in there, and that's going to be causing the diaphragm to move forwards and backwards. Now, this speaker right here is not a particularly powerful speaker. You can see on the back that it's got a couple of ratings on it here. And this one says it is an 8 ohm 3-watt speaker. Okay, so the 8 ohm is actually a term that we use impedance rather than resistance because we're dealing with alternating current here, and we'll talk more about that in second year. But basically, you can think of it as being the equivalent of an 8 ohm resistor because you've got very skinny wire and you've got a very long length of it that the electricity has to pass through. And it is a 3-watt speaker because it is capable of generating 3 watts of audio power before you start to overheat the coil in here and cause your speaker to blow up or various bad things to happen, okay? 3 watts doesn't sound that big if you're used to talking about 150 watt, 200 watt stereo systems, but as we'll also talk more when we get into amplifier circuits in second year, Audio power is logarithmic. So in order to make something sound twice as loud as our 3-watt speaker here, you actually need a speaker that's 10 times as powerful. So to make something twice as loud as this goofy little speaker here, you need a 30-watt speaker. This generates more than enough noise to be wonderfully annoying. Now, the speaker that you've got in your big bad breadboard board right here is actually a 32 ohm speaker. Okay, so 32 ohm impedance, and it is a 1-watt speaker, as I recall. So even though it's a slightly less powerful speaker, it's still going to generate more than enough noise to annoy well, roommates, spouses, probably won't annoy your kids. If you've got kids, they'll probably come and say, hey, cool, what are you doing? Show me how. And then they'll embarrass you by being better at the Arduino than you are. But that's what kids do, right? Yay, good for them. Okay, so what we're going to do is we're going to hook this up to our Arduino, and we're going to annoy the neighbors. So in the past couple projects, we've hooked up a number of interesting things to our Arduino, and we've had a lot of fun with them. We've got the LCD display hooked up right in here. We've got a potentiometer hooked in right here, one side of it going to plus 5 volts, the other side going to ground, and the middle pin I've got coming through this green wire right here is coming to my analog input A5. I'm going to leave that one in there. I've got a push button right here that is on ground on one side, so I have to use input pull up to make it work, but you can follow that yellow wire and it comes out on pin 8. And then last lesson we took a look at hooking up the LED displays right here. So we've got LEDs coming along right in here, and I'm wondering why they're not blinking at me. Oh, well, we'll get that sorted out momentarily. So we've got the LEDs coming along right in here, and we've got basically every pin on our Arduino all used up, aside from pins 0 and 1. Now, I do tend to leave pins 0 and 1 not hooked up, because if you look down here, they've got the little TX and RX written right down here. And although that's not necessarily showing up on this screen, it will definitely show up if you take a look at your Arduino. And these ones are our serial ports. So these are used for communication coming back through our USB translator chip to the USB port and into the computer. So if you put anything with too much of a load on pins 0 and 1, you may have problems using your serial print commands and problems reprogramming your main Arduino chip here, the Atmega 328. So that's perfectly fine. We're going to leave those empty. I'm just going to unplug one of these, and I want to keep the push button and the potentiometer hooked up. But aside from that, it could be pretty much anything. I'll not choose 13 maybe, because it's got an LED built into it, so I won't get as much power coming to the speaker. Let's choose 12 right here. Sorry, pin 12. Now, on your Arduino, go ahead and use whatever pin you want, and just remember that when we do our examples, you'll be hooked up to a different pin. It's easy enough to change up. Now, for hooking your speaker up, we're gonna, same thing goes with this speaker. You can see the magnet in the back. There is a coil inside there. Like I say, this coil is a little bit longer and a little bit narrower wire. It's what we call a 32 ohm impedance speaker, which means that it's really not going to draw very much current at all from your Arduino, so we don't need to hook it up with a resistor in line or anything like that, because it really does have 32 ohms resistance on its own. So I've stripped a couple wires here. One of them is black because I'm just going to plug that into ground. And I've stripped one end just a little bit longer than this white housing right here, so that I can slide it all the way through. And if you want to make sure it doesn't come loose, slide it through so that that end is just a little bit longer. And then you can take that end and just bend it and wrap it around the end of that plug. There you go. And now that's not likely to pull out on you. Okay, and then you can plug that side eventually into ground, and the red side right here, Not that it's absolutely critical that you get black and red on here, just there we go right there. And I'm going to leave that in there and bend that around like so. And I'm going to make sure that even though I've got a little bit of ground exposed right in here, it's not touching or shorting to the orange wire that I've put in here. Use whatever color wires you want, but use black for this one because it goes in to ground. And you can plug into ground on either side of your circuit. Just try to keep it nice and neat and tidy and make sure nothing's touching anywhere else. And I said I was going to hook this into pin 12 right along there. Okay, so now we've got a speaker that comes in here and it's going to be powered up by pin 12. Now, as we said, we need electricity to flow through the coil inside the speaker to get that diaphragm to move up and to move down. Okay, so what I'm going to do is I am going to make pin 12, or whatever pin you're using. It's perfectly fine to use a different pin if you've got your Arduino wired up differently. I'm going to make it into an output, and then I'm going to set it high, which is going to cause a magnetic field to build around that coil. And then I'm going to set it low, which is going to cause that magnetic field to collapse. And that's going to cause the speaker diaphragm to move up, causing a little compression of air, and then back down, causing a shock wave in the other direction. So we're going to get a wave come through the air and then move, well, not really move away from us. It's going to compress the air, and then there's going to be a low pressure area after that as the speaker diaphragm moves back a little bit. Okay, let's see how this works. Go ahead and hook your speaker up, and we'll take a look at the code in just a minute here. Well, there we go. Thank goodness for the pause button. I went and plugged my Arduino in. I was having a really hard time getting it to connect. Wouldn't show up in Device Manager, so I couldn't find out what port it was on. And after testing a few different things, it turns out to be that this cable was faulty, because when I replaced this cable with a different cable, it connects and works just fine. So if you're having troubles connecting to an Arduino anytime, just sort of go through a logical process of I've reinstalled some drivers, the CH340 drivers that should have been installed, sometimes get beat around in a Windows update or something. By and large, it's really, really reliable, and if you plug an Arduino in, it pops up. Sometimes you'll run into a problem if it's drawing too much power, so if you've got a short between power and ground. But for our purposes today, I'm going to assume everything's working perfectly for you, and you can assume that everything worked perfectly for me because I hit the pause button and you never saw me sitting here going. Alrighty, so we've got our speaker hooked into ground on our Big Bad Breadboard board, and actually it's kind of hard to see right there with the light shining down on it, but I've still got my LEDs working from last day, and as you recall, this pin right here was hooked up and making that happen, and we were flashing those on and off really quickly. So when I go and I plug in right there, we're getting tones coming up from on there, and actually if I change the number that's being displayed on here, I can make that sound come and go, because what we were doing in the past is we were pulsing LEDs on. Well, that same command that's making our LEDs turn on by running current through the LED can make current come down and run through the speaker, and can make the speaker turn on and off. So, okay, I think that's coming through on the microphone. Anyway, let's try and make this do this a little bit more intentionally, rather than just taking a look at what we had happening the last time out. Alrighty, so here we go. I've got my Arduino IDE open. I make sure I've got an Arduino Genuino Uno picked out in the bottom corner here, and let me just move that over so it all matches onto the screen nicely. And then I'm going to come in here and make sure that I've got the right COM port. And if you're not sure which COM port you're working on, again, take a look at Device Manager. So I'm on the right COM port to upload code, and now I'm just going to upload perfectly blank code to wipe off what we had on there in the past, and that should turn off our LEDs for us right there. And now we can take a look at how we can intentionally make this speaker vibrate. Okay, So I'm going to do this manually to begin with and then take a look at some ways to get going a little bit fancier with it. So in here, we are going to come in here, void setup. We're using pin 12 for our speaker. So I'll give that a name up here at the beginning, and I will call that a constant and an integer because it's going to be a number. And we'll say speaker is equal to 12. Okay, and we can leave ourselves a note, / means comment. Speaker pin is pin 12. Now, this way, you guys can have it hooked up however you want on your Arduino. If you want to hook it into pin 8, just change that to 8. And if you want to put it to A0, change that 12 to an A0, because now down here in void setup, I'm going to go pin mode speaker, okay, comma, output. So we make that into an output. And in our void loop, I'm going to come down here and just do a digital write speaker, comma, high, delay 100, digital. Remember, you got to turn it off when you're done. Speaker, comma, low, and delay 100, because if you don't have that second delay, it will immediately turn back on and the speaker won't have time to move back down. And let's take a listen to what this sounds like. I'll save my code here. And it'll compile. You'll get some messages down here. And there we go. We're getting tick, 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 tick. And so each time you're hearing a tick is when that speaker is being moved back and forth. One time the tick is coming forward, one time the tick is coming backwards, and we're getting a sound at about 10 hertz, okay, or 10 cycles per second. We'll talk about that a little bit more in just a second. Let's change this number so it goes a little bit faster. And there we go. Now that's coming up and down. That's about 100 times per second, okay, because it'll move up, wait 1/100th of a second, then move down, and very buzzy type sound. And to get really annoying, let's put 1 millisecond delays in there between the speaker times. And that actually starts to sound like a real tone. Okay. Um, Now that can get to be pretty annoying for people in the nearby vicinity. So I'm just going to unplug that speaker for just a moment. Okay. Um, you just have to remember that you unplugged it. Otherwise, you're sitting there going, why didn't my code work? And we also have a few things that we can do to make this a little bit less annoying. So let's take a look. Here's our push button pin, and we've got that routed into pin 8. So we'll just say const int button equals 8. Okay, on pin 8. Remember, these definitions and declarations go up before the void setup because they apply to the entire program. Okay, and in here in setup, the code that runs once at the beginning of the program, we're going to say pin mode button, comma, input, all in capitals, underscore, pull up, all in capitals. And remember what that pull up does is adds a pull up resistor so that our pin will read high until it is pressed, and then it will read low. So now we can come down here and we can say if digital read, okay, button. Okay, so now the brackets are around button and they are part of the digital read command. So they're saying, okay, go run the digital read function on pin number button, pin 8 in our case, okay? And then you're going to come back with a number, either 0 or 1, true or false, depending on whether or not it's pushed. If it's not pushed, it's going to come back as a 1. So if it is pushed, it's going to come back as a 0. So then we say, does that number, okay, double equals is asking the question to say, does that number equal 0? And then I'll put brackets around that, and you see that the right-hand bracket, when I put the left-hand bracket, when I put the right-hand bracket in, the left-hand bracket gets that little blue box around it so that I know that those two are connected together. So this statement is like out there, okay, well, if 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 he's pushed the button, then the button is connected to ground. So that means that we're going to get a reading of 0. And if he's not pushed the button, then we're going to get a reading of 1. So we won't execute all the code that is surrounded by these squiggle brackets, ellipses to use the more correct term. And so these have got this all surrounded in here. And then I'm going to use this auto format command. And this really helps you see what is being controlled by the if statement. So remember, really useful tools in here by clicking on the round brackets to see where our matching round brackets are, okay? But also on our squiggly brackets, if I click right near that squiggly bracket, it highlights the other one. And these ones hug this section of code right in the middle, right in there. So that controls all of them. This squiggly bracket right here matches up with this one. So this says that everything right in here, right up to there, is controlled by the void loop because that's the one that's right next to the opening bracket. Okay, same thing for the setup. So getting used to those brackets, it's really easy to do in the graphical program because you see these big orange things that come out and hug things, but really important to get them in the right place because they look like little things, but they can be really important. All right, so if the button is pressed, then we'll make the sound. Let's try uploading that. It's done uploading. And let me pop that right back into there. Aha, no sound until I press that button. Okay, there we go. I don't normally do the button thing, but I share an office with my wife and she's trying to get work done right over there. So this is just a little thing for marital harmony right now. Turn off the annoying sound except when the button's being pushed. Alrighty. Now, what's happening right in here is this delay is what's controlling the frequency of our sound. And I just want to take a little bit of a look at what that looks like in an on-off perspective, okay? So what we did at first was we came in here and I'm just going to draw a graph right here. And this is our 0-volt line and this is our 5-volt line, okay? And in other words, this is on and this is off as far as current flow through that magnetic coil. And the way that started out was different color pen right here. Was we started coming out in there and we had it off for a long period of time and then we turned it on and then we turned it off and that was 10 milliseconds to begin with, and we kept doing that over and over and over again. So this section, right from right in here, where it starts going up, to the next section where it starts going up, right in here, this is what we call one cycle of our wave. Okay, and because our wave comes in and it is either on or off, this is what we call a square wave. Okay. Now, if you're used to more harmonious sounds, what you actually will get on uh, on a little a more musical note, shall we say, is you'll get sine waves, and they'll actually come backwards and they'll dip down here and then they'll come up in here, and they'll be nice smooth waves, okay, and kind of curved, and then you'll have other frequencies laid over top of them. It gets more complex. We come back and take a look at it in more detail next year. But just some basic terms. We've got one cycle right here, and when we started out, we had that one cycle taking 100 milliseconds right here and 100 milliseconds right here. So it started out at equaling 200 milliseconds for one cycle to take place. And that means that it could happen 5 times in 1 second, because that's equal to 0.2 seconds. And if we say, well, 1 second divided by 0.2 second chunks equals 5, and that's 5 hertz. Okay, so when you see this term of hertz, all it means is how many repeating waveforms do you get into 1 second. You can also make all sorts of puns on there about, if you make bad puns, it hurts. Never mind. Okay, then we came along and we sped things up a little bit. And when we sped things up, then things would start turning on and off a lot faster. So we went from 100 millisecond delays, okay, to having 10 millisecond delays. So we'd come up in here and it would turn on, and my scale is probably going to be off right here, but it would turn on and off a whole heck of a lot faster. And when it turned on and off a whole heck of a lot faster, that resulted in a higher frequency wave. So by higher frequency, we mean that we were getting more pulses per second. Okay, so if this in here was a 10 millisecond delay, and this was a 10 millisecond delay right down here, then we're looking at a total of 20 milliseconds, or 20 thousandths of a second. Okay, so that's 0.02 seconds, and for one waveform, and that would give us 1 over 0.02 equals 50 hertz, 50 cycles per second. And then finally we came along and we set that down to 1 millisecond, and it was on and off really, really, really fast, pulsing in there 100 times faster than we first did it. And that ended up giving us a frequency of 500 hertz, because a hertz is how many cycles per second you get. Sometimes you'll see it abbreviated to CPS, or cycles per second. Now, there's a whole bunch of additional terms that come together when you start making music and you start layering things together, because if you play a frequency, a sound at one frequency and layer a sound with another frequency over top of it, and you start layering sine waves over top of square waves over top of triangular waves, you get a whole bunch of much more complex sounds that we just don't need to look at today, because our Arduino is either on or off, and that's why everything's going to sound like an arcade, is because we don't have any nice little modulation in the middle to make this turn on or off smoothly. Yeah, there's ways that you can do it. In fact, right on this board right here, I have a device that can do it. This is something called a DF Player Mini, and it's actually a $5, maybe 10, MP3 player. It's got slot for a micro SD card, and with a little bit of trickery in how you format your micro SD card, you can put sounds on there and tell your Arduino to make this chip play the sounds back for you so that you actually get nice sounding music coming out of your system. But we're not striving for that today. We're here to annoy people. Okay, so now that we understand a little bit about the frequency, let's see if we can use the potentiometer to get some variable frequencies in there. Okay, because we're going to take our potentiometer and let's add this to our code right here. And we'll say const int pot, short for potentiometer or variable resistor, equals, and of course we've got this hooked up to our analog input side, okay? And it's got to come to the analog input side down here because this is where we have our analog to digital converter, so we can do our analog read command over here, and this one's coming in on pin A5. It's called A5, so we know it's on the analog side of things. Okay, and we can say that doesn't have to be A5. You could choose any of your analog sides right here. We don't have to define that as an input, but seeing as how we've got space to do it, we may as well be a little bit redundant. We don't want input pull up on there, okay, because we're just reading this. It's not a switch. In fact, we've got positive and ground over here. It's going to be somewhere between 0 and 5 volts. And what we're going to do is we're going to come right down here, and instead of delaying by 1 millisecond, what we're going to do is we are going to say, let's do a delay of analog read brackets pot. So again, double check your brackets as you type that in there. And right on here, when I click next to here, it goes to the matching round bracket, goes to the matching round bracket. And then I put the same command right in here. Okay, so what's going to happen now is when it comes to this statement right in here, it's going to say, hey, what voltage is coming in on pin 5? It's going to turn that number that's somewhere between 0 and 5 volts, depending on how I've turned my potentiometer, into a number between 0 and 1023, because we have a 10-bit analog digital converter built into our Arduino right here. And then it's going to take that number that it just read right in there, because this is inside these brackets, and it's going to pass that number over to the delay command and say, hey, sit there and do nothing for that many milliseconds. So we can upload that on there. And it's done uploading. And now push my button to turn it on. And you can hear it's just going tick, 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 tick. So I'm getting a very high delay. Oh, it slowed down. And I'm not getting down into the really low sounds right on there, or the really high pitched sounds. So I'd like to have my delay run a little bit faster. Now, our standard delay routine just takes that number and does a delay in milliseconds. But if we want delay to run faster, there is a faster way to do that. And I recommend that you always look back and spend some time taking a look at the reference file for the Arduino, because in here you find all sorts of interesting tidbits of information. At least you will as soon as I can get this to shrink down and fit onto the screen so you can see it all right there. Okay, there we go. There we go. Just got a little over enthusiastic about making it nice and big there on the top of the screen. Okay, so down in here, and take a look through here and you find all sorts of interesting commands. And under your time section in here, there's delay, but right underneath that, you'll see that there's delay microseconds. And that's because we can actually delay 1,000 times faster than that delay statement does. So let's go back in here and type in delay. Okay, and notice how the color changes when I type it in correctly. Okay, and so that means when the color changes, that means that the Arduino IDE recognizes the word that you've typed in. So if you've got a spelling error in there, it's going to be the wrong color, okay? But if you spell it correctly, it's going to be orange. I don't know why orange. Let's upload that and see what happens. Now keep in mind that 1,000 microseconds is 1 millisecond. Okay, so milliseconds, millis is 10 to the minus 3, micro is 10 to the minus 6. It's like kilo and mega on the other side of the scale. So make sure you know your metric prefixes. Ooh, curious how that's coming through on this microphone right here. The microphone's supposed to have noise canceling features, so I don't think it's going to be able to cancel that out. As you can see, I'm having an inordinate amount of fun with that. And I hope you are too. So there you go. Now we've got an interactive little synthesizer. You would have been a big hit in the recording studios of the 1960s if you could do this. Right, sorry, too much fun. So we've got a pretty simple way to start making things come together in there. And you can even do really cool stuff. You'll remember a little while back that we had this little device right here, the photoresistor. Pop your Arduino, or sorry, pop your potentiometer out right here. This is going to work almost the exact same way. And we're going to hook that up between the sensing pin and the +5. And then find a resistor. This one is brown, green, orange. Try to find an orange in that third band. We're looking for something in the thousands of ohms capacity. Try any resistor, really, but make sure you've got a resistor in there. This creates something called a voltage divider, where we've got a resistance on this side and a resistance on this side, and that's going to cause a different value to come out right in here. And I hope that came through on there. I mean, just the hope. I mean, the smile on my face should be enough to tell you that's awesome. And if you've got that working for you, you're part way to creating a fake theremin. Make 5 fingers. You can see why this class is fun. It's one of my favorites. Okay, so now we've got interactive sounds coming off the Arduino, but I promised you that before we were done, we would have the Arduino Symphony Orchestra up and running. And in order to do that, you need to play some pre-recorded sounds. Now, there's all sorts of ways that you can go about doing this, but just pause me for a moment, okay? And just Google Arduino music, see what you get, and see if you can make an Arduino music program get up and running all by yourself without any further guidance. Just remember that you may need to tweak it to tell it which pin your speaker is plugged into, okay? Go ahead and give that a shot. I'll hit pause too, and then you can go ahead and give that. Well, how'd you do? Did you find something interesting? Of course, this is the one I found. The emperor is not as forgiving as I am. So while we've got the Imperial March playing in the background here, let's take a little bit of a look at how they managed to do it, where I found this code, and why this is such a fun day to have students engaged in doing this project in the shop. Because as soon as somebody gets that playing, somebody else is like, well, if they can do it, I can do it. And they start hunting around, and let's take a look at where we found this song and where you can get things. Let's go right back here. So I typed in, Google is amazing. Arduino music. And, you could go to the first one that comes up. There's videos on here that talk about how to do this. Many of them much shorter than mine, no doubt. And then you can come down here, but this is one that I saw. So if you see this one, Dragosimchana. Oh, uh, Dragosimchana. There we go. Go ahead and take a look at that. And this seems to be a really nice collection of songs right in here. And there you go. You can see he's just got, now this is a type of speaker called a Piezo Buzzer. Instead of using a coil and a magnetic speaker, this actually uses even less current. And anytime you see the term piezo, that refers to a type of crystal that changes its size when a voltage is applied to it. So buried inside there is a tiny little crystal that when you hit it with a voltage, it expands, and when you hit it with a negative voltage, it contracts a little bit, and you can make that vibrate back and forth to vibrate a thin little plate. I think we get slightly nicer sound off of the more classic speakers, but both work just great. Anyway, you'll also notice that he's hooked up on pin 12 right here and has some instructions right along here and has a whole bunch of music from movies and all sorts of places where you can come along here. And let's see, where is something down here? Does he not have the Nintendo song in here somewhere? Um, Anyways, he's got all sorts. Oh, there we go. Mario Brothers is in there. Legend of Zelda, Doom. So video games are in there. Let's take a look at a classical piece. Let's take the Pachelbel's Canon. Now, when you click on the music that he's got in here, it will take you to this site called GitHub. And as you get into working with microcontrollers, you're going to see a lot of people referring to GitHub. GitHub is a public shared repository where if you want to share code with people and allow people to work on it and make changes to modify and improve your code, then you can put it up here. And it's been really great for open source and collaborative projects to develop things on the code sharing site. But you can come in here and you can see all the code is listed out just as text right in here. It's nothing too fancy. There's your void loop. So you need to come right down to the end of void loop right in here. And if you highlight all that code, make sure you get all of it right up to the very beginning here, but you don't want this part. You just want right to that line 1, okay? And you can just copy that and open up your Arduino IDE and say File, New. Delete the stuff that's all in there because you want something completely blank, and drop that code right in there. And here we go, Pachelbel's Canon. You should be able to upload that. What do we have to do before we upload it? Take a look in here, and somewhere in here, there's this. Remember I said they will be using a different pin for their speaker. Okay, come down here, and sometimes the code uses the term buzzer, sometimes they use the term pin, sometimes they use speaker, but you'll find this in here, and I'm hooked into pin 12, you're hooked into whatever you want, and now go ahead and upload it to your Arduino, and that will knock the Imperial March right off of mine. I don't know if I quite like his interpretations of this. I think that needs to speed up a little bit. So see, he's got this thing in here for tempo, and he says change this to make the song slower or faster. Let's try changing the tempo. He doesn't say which one makes it faster, but I think if I put 80 in there, oh, there we go. That's sounding better. Let's see if 80 makes it go a little faster. That's a little faster. So you can play around with some of the settings in here. Now let's take a look at some of the things that are going on in here while that plays in the background. Okay, so a lot of the music code starts with all these defines. Okay, now if you take a look at sheet music, or if you've played an instrument before, you know that there's the notes A, B, C, D, E, F, and G. So 8 notes in an octave. Okay, and there's different octaves along the piano keyboard or along your guitar. And so the lowest octave is going to be octave 0. So that's our lowest frequency. So that's off with your bass hand on your left hand on the piano keyboard. And you can see that there's a frequency in here, and this is only 31 hertz. Now that kind of makes sense. The range of hearing that humans can hear is between 20 hertz and 20 kilohertz. So 20 to 20,000 hertz. So 30 is getting down low on what we can hear. Um, He's got S in here for sharp. So those of you who have played some music, when you've got C sharp, that's going to be on this octave at a frequency of about 35 hertz, and D is going to be at 37 hertz. Now, what's interesting right in here, if as I look at C1 and C2, okay, you can see that the frequency between C1 and C2 within the limits of integer math actually doubles. And if I come up here to C3, it doubles again, 65 up to 130. Okay, that is part of the magic beauty where math and physics meets art, and the octaves in a piano keyboard or any form of musical note or singing for that matter are set up so that each octave doubles the frequency of the octave beneath it. So if I come up to C4, 262 is double 131, and C5, again, twice that. So each time you go up an octave, your frequencies keep doubling. So he's got all these notes laid out all the way up. So 8 octaves in here, and comes into the um, our highest one is going to be C around 4 kilohertz, which is probably about as high as we want to go, because human hearing starts to drop off as we start getting into the higher frequencies, particularly as you get a little bit older. So we changed our pin so that that would go in here. And now you can see right in here, he's got the entire sequence of notes played up right in here. So you could come in and you could start editing these up. You do have to follow the format though. Okay, so he's got this a little description right in here saying 4 means a quarter note, so a shorter note, 8th and 18th, and 16 a 16th. So right in here, here's the note F sharp from the 4th frequency, and 2, that means it's going to be a half note. Okay, so a longer tone. And then we come down here when things start picking up, you'll see that they goes down to 8th notes. And does it get any faster than 8th notes? No. So there's all the notes in there, and there's their delays. And then he comes in here and he makes a variable that takes this data and then plays it back one note after the other down here using something called an array. And we haven't taken a look at arrays yet, but it's a way to store information, numbers in a big long sequence, and then pull those numbers out one after the other and store things back in there. It's really useful for storing large amount of data, like large amounts of notes. Okay, so then he comes down here and now he uses the tone command. Okay, I was showing you how to create sounds just using digitalWrite, but just as there's little shortcut commands for all sorts of things in Arduino. Take a look in your reference, and in here you will find the tone command somewhere in here. Bits and bytes. Okay, if you're having problems finding it, you can just search the Arduino website up here and say, tell me about tone. And that brings up tone in your Arduino reference, and it tells you how it's going to play. Okay, and it tells you a little thing that it may mess up pins 3 and 11 just from the way that it works. And it'll come in here. It says tell it what pin you want and what frequency you want, or you can even tell it to play for a certain duration. And then it tells you other commands that are tied into it and examples of where you might be able to try that. So the Arduino reference, really helpful place as you're learning the Arduino to look things up. And of course, the internet in general, really useful place to hook things up. So hopefully you're having your own little Arduino symphony at home over the next couple of days. You find some songs that you like and that only moderately annoy those who are close to you. And your big bad breadboard board is working and coming along really nicely for you. Now, if for some reason you run into a problem with that working on your big bad breadboard board, or you don't have a big bad breadboard board, don't worry, because let me just shrink this window down and get it out of the way a bit, because Tinkercad is here for you. And if we come over to Tinkercad, Tinkercad has something all set up right in here. And in fact, if you come into Tinkercad and let's get rid of the code window right here. And under your components, if you look for all your components in here and scroll down a little bit, you will find somewhere, actually you may have to choose the Arduino components. There we go, down here. You'll see one that's called Tone Melody, and you can just drag that out there and you can see that's what I've got floating around. I don't need two of them, thank you. Okay, get that out of my design. And then if you take a look at the code, Tone Melody actually comes with some code already installed right here, and it uses a simplified or shortened version of what we were just looking at on the longer musical scores. So on here, we've got only 4 or 5 notes that it's going to play. And here you can see, again, it's using the quarter eighth notes duration. So those of you musically oriented, you've looked at sheet music, you know what an eighth note is, you know what a 16th note is. And it's got some good commentary on here explaining how it works. And this is kind of neat. When you start the simulation, stop the simulation right in there. It's amazing. Tinkercad actually simulates the speaker for you. So everything that we've tried, you can take that code right out of your Arduino right on here and set it up exactly the same way. Let's come in here. It's not melody that I want. I want, here we go. Select edit, select all from our Arduino code. Copy that right there and bring it over to your Tinkercad. Delete everything out of here. Delete everything out of there. Copy everything into right there. And just make sure this is on pin 8. So make sure you update your code so that you're using the correct pin. And you can start your simulation on here. I'm going to stop that simulation. But there you go. You can have music playing away lovely in there. You could bring in the the potentiometer and the button like we had hooked up, and you can have your code so that as you adjust the potentiometer, you adjust the code. You can have your fake theremin in there, so you're using your photoresistor, and as you block the light on there, you change the resistance right here, which, because you're in a voltage divider, changes the voltage right here, just like spinning your potentiometer back and forth. That comes back in there, and you can go ahead and you can make a whole bunch of really annoying noises, which I think is kind of fun. So anyway, it's not quite as fun to do this at home where you don't have a whole bunch of classmates there to annoy, and the people that you annoy at home you actually have to live with. But anyway, spring break is coming up, and maybe you can go ahead and create some neat music on here. If you wanted to get really fancy on here, what you could actually do is you could use your photoresistor and shine a light on it from the other side of the other side of the room, and you could have it hooked up so that that light is shining really brightly on there. And if somebody walks through that light beam, then the photoresistor detects that the light beam has been broken, and then it starts playing some annoying music. So you could play annoying music whenever somebody walked into the classroom. Uh, all sorts of different things that you can hook this up to do. And of course, if you compact it all down into a tiny little package, then you can hide it somewhere and just tell it to do it every, 20 minutes or so. Only play about 3 tones for about 5 seconds. See if anybody can find it. Just don't do that in my shop, please. Anyway, I think that gives you a good idea on how to make some sounds on the Arduino. I hope you have a lot of fun with that. And yeah, be interested to see what you get. I'll give you a space to upload some of that after spring break. So give it a try now and make sure you can get this working for you. Thank you very much, and have a good day, a musical day, a fun day.